this question asks us to approximate the points where the graphs intersect. So go ahead and use a graphing calculator. Like I use Desmos, I graph the two functions, and I cross here and here. So we got an approximation of the x coordinates. And then we're supposed to approximate the area between their graphs, accurate to 3 decimal places. So we want this area. So the blue function was g of x. G of x. And then the red function is f of x. And we can't just integrate from negative 0.763 to 763 of g of x, because that would just give us the top part. Because when you integrate with respect to x, that's just going to tell you the area between your graph and the x-axis. I think I know what we can do, though. So we want to integrate g of x that's going to tell us the top area, and then we want to add to that the integral, and it also says approximate again. It says approximate the area. I wonder if they don't want a definite integral. So we want to do the same limits of integration, 0.763. And then we want to, if we integrate for f of x, then we're finding the area under here. So if we add those together, then we'll have the total area under the curve. But you'll want to take the absolute value, because this is going to be negative, right? For f of x, it's below the x-axis. That means it's going to give us negative area, but we want this total two-dimensional area, so we got to make sure we take the absolute value. So the second one's no problem. And in the textbook, we haven't yet done this part. Like, you can evaluate this integral without using a calculator. You'd want to rewrite it as 1 plus 4x squared over square root of 1 plus 4x squared over 1 plus 4x squared being squared. And I think at some point we'd have to use a trig substitution. But we haven't done that. That's in chapter 7 of the textbook. So instead, I think what this question is trying to do is, with the, when I keep saying approximate the area, we could use those approximation techniques we've already done, like the left endpoint and right endpoint sums, and then we need to 3 decimal places. So for these integrals, we use the midpoint is usually best if you can. We can use a midpoint Riemann sum, which I think I can find a calculator online. So if you go to Google and type it, midpoint Riemann sum calculator, any of these will do. The point is, with this type of integral, this one is particularly difficult, and we need a technique we haven't yet done in the class. So I think that's why they want us to approximate the area. So you could do it by hand, but I mean, in order to get it marked right on WebAssign, you'd have to take a ton of small subintervals, so that'd just take too long. So it's from negative 0.763 to 7.763. And our function was 1 plus 4x squared, so then negative 3/2. Subintervals will just set it to 100, and then it really doesn't matter when you have this many. Trapezoidal rule is a little more accurate, but I don't think we've done that yet in this course. So using the midpoint rule, what do we got? It looks like that area is here. They said 3 decimal places, but we'll take some extra just to be safe. Okay, so that's that one, and then we want to do 2x squared minus 1. And then same interval. And remember, we're doing the absolute value, so if you add those together, 1.770 is what I got. Yeah, they got the same thing.